In Lesson 9, Paul challenged us to add the local time and date to our GPS report. This means we now have way more data than will fit on the OLED screen. Our Lesson 10 assignment was to expand the OLED to another screen, then add altitude to our report. Let's deal with the OLED first. The green and red push buttons are now part of the project. The logic in this assignment creates an interrupt for each push button. We also add a new variable to the program, OLED page, initially set to 1. Green button ISR will increment OLED page. Red button ISR will decrement OLED page. In this assignment, OLED page ranges from values 1 to 4. The display logic contains if-else-if clauses based on the value of OLED page. GPS data can now be spread across the 4 or more OLED pages. Managing time and date turns out to be a bit more complicated. Time and date are reported by the GPS in Coordinated Universal Time, abbreviated as UTC. UTC is the time at the prime meridian, which is longitude 0 degrees. In general, users not living at longitude 0 must add a correction factor to UTC time to calculate their local time. The correction factor is negative for users west of longitude 0 and positive for users east of longitude 0. The further a user is from longitude 0, the larger the correction factor. As examples, the correction factor for Toronto, Ontario is minus 4 hours, and for the island of Mauritius is plus 4 hours. Unfortunately, simply applying the correction factor is not sufficient. If we only added the correction factor, users in western longitudes would face two complications. The first being that the UTC date reported by the GPS changes to tomorrow's date at midnight UTC, which will appear to be early to any Western users. For example, the date will change at 8 o'clock at night, Toronto time, not midnight. The Pico logic would have to continue reporting UTC date minus 1 day until 0 hour local time. There is an added complication at a month boundary. In order to calculate UTC date minus 1 day at a month boundary, the logic would need to know whether the previous month had 28 or 30 or 31 days. Also, keep in mind that if UTC year is a leap year, and UTC month is March, and UTC day is 1, the previous day would be the 29th of February, not the 28th. The second complication is that local time would be reported as negative for some hours. For example, until 4 o'clock UTC in Toronto. The Pico logic would have to add 24 to UTC hours whenever UTC time is less than the correction factor. Users in eastern longitudes face similar complications. As before, the UTC date changes to tomorrow's date at 0 hour UTC. This will appear to be late to eastern users. For example, the date will change at 4 in the morning, Mauritius time, not midnight. The Pico logic would have to start reporting UTC date plus 1 day at 0 hours local time. Our earlier concerns about month boundaries and leap years all apply here as well. The second complication for users in eastern longitudes is that local time will be greater than 23 hours, 59 minutes, 59 seconds for some hours. For example, until 0 hours UTC, as seen in Mauritius. Pico logic would have to subtract 24 from UTC hours when UTC time is greater than 24 minus the correction factor. Imagine the rat's nest of if statements required to deal with all these exceptions. I found an alternative approach using time.makeTime and time.localTime. Assume that UTC-YR, UTC-MO, etc. represent the UTC year, month, day, and so on. The time.makeTime function converts UTC time and date into the number of seconds since the epoch, which is 0 hour on January 1st, 2000. We calculate the current UTC time and date in seconds as shown here. The last two entries in this tuple represent day of week and day of year values and can be ignored for our purposes here. We convert UTC in seconds to local time in seconds by adding our UTC offset, also expressed in seconds, as shown here. Now we use the time.localTime function to convert local time in seconds back to a local time and date tuple with the formula shown here. The beauty of this solution is that the time.makeTime and time.localTime functions manage all the end of month and leap year exceptions that we just highlighted. I tested this with all the troublesome time and date combinations I could think of, and it works. Let's look at the code. The logic in this program has changed somewhat compared to Lesson 8, but the only hardware change is the addition of the green and red push buttons. The Lesson 9-10 imports are the same as Lesson 8. Here we declare the pins used for the green and red push buttons. And here we create two new objects, green button and red button. These buttons are connected to the 3.3 volt rail, so they use internal pull-down resistors. We declare our variables on lines 34 to 66. These are the Lesson 8 variables with the addition of altitude, course over ground, magnetic heading, UTC and local time and date items in the GPS dictionary, and the OLED page variable. OLED configuration is identical to Lesson 8. Fixed status logic has not changed since Lesson 6. Fixed status is defined as an interrupt on line 91. Whenever the fixed LED on the GPS module comes on, the fixed status pin goes high, triggering the interrupt and calling the fixed status ISR defined on line 77. The got-a-fix variable tracks whether we have a fix or not based on the period of that blinking. The read GPS on Core 1 function has not changed since Lesson 8. It waits for a fix, empties the UART buffer to get a clean start, then builds the raw sentence variable by detecting the known leading and closing characters in GPS NEMA sentences, $, and the new line escape character. The heartbeat feature signals the user that Core 1 is still running with a symbol on the bottom line of the OLED. This function can recover from losing a fix, and it will come to a graceful halt when the user presses Ctrl-C. The push button logic is new in this lesson. Each button will generate its own interrupt. The green button interrupt is defined on line 152. The red button interrupt is defined on line 176. Both interrupts will trigger on a rising pulse when the button is pushed or a falling pulse when the button is released. When either interrupt triggers, the corresponding interrupt service routine, or ISR, will be called. Each ISR keeps track of its button's current and previous button value, the current and previous press time, and the current and previous release time. The logic guarantees bounce-free operation. Pressing the green button will increment OLED page on line 139. Pressing the red button will decrement OLED page on line 163. OLED page rolls over at either 0 or 4. Lesson 9 and 10 also contains the GPS command suggested by another of Paul's viewers. It enables the transmission of GPVTG NEMA sentences, which some users reported to be missing. The initial OLED messages are the same as Lesson 8. Initial values for the push buttons are new, and lines 212 to 215 are the same as Lesson 8. The general layout of the try except clause containing the main while true loop has not changed. What is new is the extraction of speed, course over ground, and UTC date information from the GPRMC NEMA sentence. Also new is the extraction of UTC time from element 1 of GPGGA sentences. If we have valid UTC year, month, and day values, the logic on lines 236 to 242 implements the calculations discussed in the introduction and updates the local date and local time dictionary items. Otherwise, placeholders are loaded into the local date and local time elements. As in previous lessons, we extract lat and lon data from GPGGA sentences, negating it as necessary. We also extract the quality reading from element 6. New in this lesson is the extraction of altitude data from element 9. Now that we're blessed with virtually unlimited OLED pages, we can extract the list of satellites being used by the GPS and configure them in lists that make them easier to display on the OLED. This is new logic in lesson 9 and 10. GPVTG data extraction is the same here as it was in lesson 8. The OLED display logic has expanded to allow the OLED page variable to determine which GPS parameters are displayed. The current page number has been added to the heartbeat and fix parameters displayed on the last line of the OLED. The accept clause has not changed since lesson 8. When the user presses Ctrl+C, we message the user, set stop core 1 to true, and wait for core 1 is stopped to become true. Finally, we deinitialize the GPS, sleep briefly, then message the user that the program has stopped cleanly. Let's see how it works. We message the user when the program starts. Once we achieve a fix, we parse our GPS data and display it on various pages on the OLED. The green and red push buttons allow us to page forward and back through our data. Notice the page number on the right side of the last line of the OLED. And the program exits cleanly when the user presses Ctrl+C. Well, that's it for this assignment. Any and all comments are welcome. Don't forget to like or dislike the video before you go. And feel free to subscribe. Don't forget the notification bell. We'll talk to you next time.